أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني يفقهوا قولي رب يسر ولا تعسر وتمم بالخير السلام عليكم ورحمة الله وبركاته आज today our linear control systems lecture number 14. So in this lecture we will be studying the observable canonical form. So in this observable canonical form, we will be treating the transfer function a little bit differently as we have done for the controllable canonical form. So let's understand this procedure with the help of an example. So we have say the transfer function g of s is given as ysf over r of s, which is equal to 2s plus 5 by s square plus 7s plus 10. So in this method, what we will do is we will just rearrange this transfer function such that as s square plus 7s plus 10, we will cross multiply these terms, and that will be 2s plus 5 into r of s. So taking the inverse Laplace transform, taking inverse Laplace transform. So what we will get is y double dot plus 7y dot plus 10y, which is equal to 2r dot plus 5r. And we will use some operator to describe this derivative in this equation. So let the differential operator be used as, so that will be d square y plus 7 dy plus 10y, and it will be 2dr plus 5r. So that can be written as 7d plus 10, and we will take this y here. Similarly here 2d plus 5, and we will take out r from here. Now we will leave this highest order term here, and we will take all the terms on the other side. So that will be d square, and that will be y sorry so that will be simply d square y, and that will be d times 2r minus 7y plus 5r minus 10y. So we have just rearranged the terms with the d and without the differential operator. Now here we will take this d, and d inverse will be d that will be transferred to the other side. So it will be d minus 1 2r minus 7y plus d minus 2 5r minus 10y. Okay, so this is here what we have y. Now let's define two states for this equation, and we say that let x1 is equal to y, and x2, these are the r2 state variables. So according to this, then what we can do is x1 is equal to y. So this equation we can write it as x1, which is equal to d inverse 2r minus 7y plus d minus 2 and 5r minus 10y. Now if we differentiate this equation, so differentiating this equation, so what we will get x1 dot, and that will be equal to this d inverse which is the anti-derivative, so that will be cancelled with the derivative, so it will be 2r minus 7y and that will be d minus 1 5r minus 10y. Now let we define this portion, this part as x2. So that is defined as d inverse 5r minus 10y. So this equation will become x1 dot is equal to 2r minus 7. Now y is x1, so that will be x1 and plus this whole term is x2. So now using this equation x2 is equal to d inverse 5r minus 10y, we will differentiate this equation. So differentiate. So when we will differentiate, it will be x2 dot, and this anti-derivative will be diminished with the derivative. So that will be 5r minus and this 10y. So y can be written as x1. So now we have these two equations. Here we can use them to write them in a matrix form. So x1, x2 dot. Okay. So x1 dot is minus 7x1 plus x2, so minus 7x1 and 1 times x2, and here it will be x1 x2 plus we have the term with the r, and that is 2r. Okay, so we will have this 2. So 2, and then we will be having r. So from the x2 equation, what we will get minus 10, and this x2 is 0, and for r we have this 5 times r. And similarly for the output equation, we have defined as y is equal to x1. So it means that it will be 1 0 and x1 x2. So now this is the observable canonical form, and we will see these matrices have the different format, different form as compared to the controllable canonical form. So in this system matrix A, we can see that the first column are the coefficients of the denominator polynomial of transfer function with negative signs, and the elements of the other columns are either 0 or 1. And also the elements of matrix B are the coefficients of the numerator polynomial of the transfer function. And similarly, the C matrix, which is output matrix, the first element of the output row matrix C is 1, and all other elements will be 0. So, let's solve another example with the third order system. So let's this example, which is g of s is equal to y of s over r of s. So that will be that is equal to 5s square plus 14s plus 8 divided by s cube plus 9s square plus 23s plus 15. Okay, so now let's solve this. Again we will cross multiply it, and we will have s cube plus 9s square plus 23s plus 15 into y of s, and on this side it will be 5s square plus 14s plus 8 into r of s. Now taking the inverse Laplace transform, okay, so we will take the inverse Laplace transform of this equation. So what we will get is this will be y triple dot, which is a third order, plus 9 y double dot plus 23 y dot plus 15 y, and that is equal to, on the other side it will be 5 r double dot plus 14 r dot plus 8 r. Now again we will use differential operator d, using differential operator d. So what we will get is d 3y plus 9 d square y plus 23 dy plus 15y, and here it will be 5t square y plus 14 dy plus 8r. Okay, one thing you might have noticed that all the transfer functions so far we are using are the strictly proper transfer functions. Okay, so in strictly proper transfer function, the order of the denominator is always greater than the order of the numerator. Now, again, we will leave it here and we'll take all the terms there. 9t square y minus 23ty minus 15y plus 5t square y plus 14 dy plus 8r. Now we will have collect all the terms of d square and d and without the differential operator terms separately. So here we have this d square and d square here. Sorry, one problem, one mistake that I made here. This is not y. Again, similarly y, not y here. So this is r, r, r. Okay. Now it will be d square. How that will be 5r minus 9y d square plus 14r minus 23y d and minus plus 8r minus 15. Now we will take this derivative differential operator on the other side, so it will be d inverse 5r means derivative 9y, and it will be d minus 2 14r minus 23y, and it will be d minus 3 8r minus 15y. Now let's define some state variables. So we define them as let x1 is equal to y, and then x2 and x3 are state variables. So these state variables, with these state variables, we can write this equation here as this will be x1, which is equal to d inverse 5r minus 9x1 plus d inverse 2 14r minus 23x1, and then it is minus 3 8r minus 15x1. Now differentiate this equation. So we will differentiate it. Differentiate this equation, so we will get x1 dot, which is equal to, then this antiderivative will be removed, 5r minus 9x1, and then plus this will be d inverse, and it will be 14r minus 23x1 plus d minus 2 8r minus 15. Okay, now what we will do is we have taken this differential. Now we define let this x2 is equal to d inverse 14r minus 23 x1 plus d minus 2 8r minus 15 x1. So now put this x2 here. So what we will get this equation from here, it will be x1 dot will be simply then is equal to 5r minus 9x1 plus x2. Okay, so this we call it as the, say, equation A. Okay, now using this equation, x2 is d inverse 14r minus 23x1 plus d minus 2 8r minus 15x1. Now again differentiating this, equation. So what we will get, x2 dot, which will be equal to this antiderivative will be removed, and it will be 14r minus 23x1 um, 43x1 plus that will be d minus 1, 8r minus 15x1. Now again we assume that let x3 is equal to d inverse 8r minus 15x1. So this equation can be written as then x2 dot is equal to 14r minus 23x1 plus x3. Okay. Now we call this as equation B. Similarly, we will write for this uh, from this equation we differentiate. If you just differentiate it, what we will get x3 dot, which will be equal to 8r minus 15x1. Now we have these three equations, x1 dot, x2 dot, and x3 dot. So we can write down their matrix in the matrix form. We can write them in as x1 dot, x2 dot, x3 dot in the matrices form. So this will be a 3 by 3 matrix. So this is minus 9, 9, 1, 0, minus 23, 0, 1, minus 15, 0, 0. And this is x1, x2, x3. Three state variables plus 5, 14, 8 times r. Now the output equation as we have written is y is equal to x1, so it will be 1 0 0 x1 x2 x3. Now again if we just look at this system matrix A, we can observe that the first column here contains the coefficients of the denominator polynomial of transfer function with negative signs. Okay, and the elements of and other elements are the either 0 or 1. Also, the elements of the column matrix B are the coefficients of numerator polynomial of transfer function. Here we can see, and the first element of the output matrix C is 1, and all other elements we can see are the 0. So in this way we have seen the other way how we have manipulated the transfer function so that we can obtain another form of the state space. So that's this is if we have state space given in this form, so we call that as the observable canonical form. So I hope you have understood so far but still if you have any questions, please feel free to ask in the comment section. Take care of yourself. May Allah bless you. Assalamu alaikum wa rahmatullahi wa barakatuh.